So here we see a fresh circuit where we have input signal E in applied across these two terminals as shown, and there is a parallel network of LNC and output is across these 2 points, and load RL is connected at the output as shown. So now there are many things we can analyze for this circuit. First is your voltage and the current and the impedance. So you have V in, you have V out, so you actually can calculate all these voltages. So for example, you write a KVL in the loop, and that gives you expression V in minus the current flowing through this effective impedance of LNC multiplied by the value of that effective impedance. So the impedance of L and C, let's say ZLC, would be XL in parallel with XC. So you will write XL in parallel with XC multiplied by the current. So that's the voltage drop across this L and C network right here. Okay, and this is the current that is flowing and we are calculating. Now the same current flows through the load RL, so you subtract that drop as well, minus RL multiplied by I, and then you equate it to 0. So that is how you calculate. Now output is taken across the load connected, so you will write, so this is your output voltage VL, so VL would be I times RL. Okay, and I is your V over Z in, and V is your V in, that is this input, and I is your I in, that is the input current that is flowing inside the loop, and Z in would be, let me calculate the Z in. So V in divided by Z in would be the sum of the resistance of RL plus the effective impedance of LNC network, which is ZLC. So it would be RL plus ZLC. So that is how you actually can see that you are able to calculate the voltages, output voltage, input voltage, and currents. Similarly, you can calculate by applying the voltage division rule. The voltage across the load, that is VL, would be, just apply a voltage division rule, which is the RL divided by RL plus ZLC, which is the effective impedance of LC network right here, multiplied by V in. Once you have that, you can actually get the voltage gain, which is the ratio of output voltage divided by input voltage. So it is RL divided by RL plus ZLC. So you basically take the V in the denominator of this equation, and that is how precisely we have indicated here. So we are able to calculate the effective impedance, voltage gain, output voltage, input current, etc. We are able to apply the Kirchhoff's voltage law also to get this very first equation. Kirchhoff voltage law allows us to calculate the drop across each of the components and sum them all and equate it to 0. That is what the KVL says. Similarly, you look at the input side of the circuit by applying the open circuit rule. So you have the open terminals and you look into the circuit to calculate Z in. So it is your LNCR in parallel, so that's the effective network ZLC plus RL in combination with that. So ZLC is your XL into XC divided by XL plus XC plus RL. XL is your omega L and XC is your 1 over omega C. Then in the denominator you write those values again and keep on solving that and simplifying it. So this is how you see your impedance is a function of frequency, and this is how it varies. Now if you are asked to decide the output impedance of this network, which is the impedance when you look into the circuit from the output side, and it is CO. So what you do is you remove the resistance RL, and then your circuit is open circuited at these 2 points, and then you look inside the circuit from these 2 terminals, and what you see is the LNC in parallel. So that's the Z naught would be your XL in parallel with XC. That is your effective output impedance of this network. So if you do the analysis and calculate the voltage gain VO or VL divided by V in, how it varies with respect to frequency, and impedances ZO and Z in, how they vary with respect to frequency, you can understand and know the frequency response of this circuit, and you can see what kind of filter it is acting as, whether it's a low pass filter or high pass filter and so on. So hope you like this video, share with others.